Okay, problem 13. We're going to find the area between two functions where x is a function of y, and I don't like to get these functions to be too complicated because they're usually I keep lines and parabolas is all I work with on these. They can be a little tricky otherwise, especially for graphing purposes. If you know it's going to be a line and parabola, anytime you have x equals y squared, it's going to be, if the y squared is positive, the parabola opens to the right. If it's negative, it'll open to the left. And you could get it by kind of plotting some points. So in other words, we have x equals y plus 4, so we know that we have a line, which is easy to graph. And then if you know the parabola's coming to the right, you don't have to even really sketch it perfectly, because you could just kind of go, okay, well, get the line right, obviously. Get the line like this. And if you know you got a parabola doing this, that's fine. And we'll be finding that area. But so the key thing we have to do really is just find these points of intersection. And these kind of problems I never make where they have more than two regions of area. In other words, like some of the other ones I do, where y is a function of x. So you can kind of get away without doing all that. Just for grins there, I showed how to graph them. But don't feel like you have to do that. You actually, it looks like I didn't actually show the work. But anyway, I did it correctly, but you have to take the y squared equation and solve it in terms of x and get the plus and minus radical of it. You have to get two equations that actually draws each half of the parabola and then the line. So that's what sketching this is, those three equations, because it's two half parabolas. But anyway, forget all that. As long as you know it goes to the right like that. Actually, it probably wouldn't matter whether it went right or left as long as the line coming through there. It's just set these two equations equal to each other. See, I moved the 1 over, so I have x equals 2y squared plus 1, and then x equals y plus 4. Set them equal to each other. These are pretty much set up to be factorable for the most part, so shouldn't be too difficult. And you'll get 3 halves and -1 as your two y values, which would be the -1's the lower dot, 3 halves is the upper dot. Because in terms of y, we're integrating lower to upper instead of left to right. A to b on the x-axis whenever it's a function of x. So you need to put the one that's on the right first, the one that's on the left second. But the good news is, since I'm only promising these are going to be, just two equations, one area, if you get these backwards, just realize you're going to get the negative of the right answer. That means the right answer will be the other one. So, but technically this is the proper setup. Y plus 4 minus 2y squared plus 1. That condenses into negative 2y squared plus y plus 3. Now you can use the F&Int feature of your calculator. You don't have to, just because it's y here, when you're just integrating, you can integrate this in terms of x. But mathematically, I'm not saying that y equals and x equals are the same equation. That's not what I'm saying. But if you're integrating a variable there, in other words, this variable could be happy face and it wouldn't matter. It doesn't matter as far as the numerical calculation. So this, I have negative 2x squared plus x plus 3, which would be from down here, negative 2y squared plus y plus 3. This is obviously an older operating system. You have to tell it the variable x here. The newer ones, if you do the F&Int, it brings up the integral symbol, and then you put in everything you need. So a lot more intuitive, but this just kind of shows the old way to do it. New way is easier. And I'll pause for a second, then I'll add so I won't waste any time with the video running, and I'll add a screen of what the new way to do it would look like. So, and you can see the result now that I put in the newer calculator. That's kind of small there. We could zoom in on that, but yeah, you see it's much more normal looking, I guess you would say, than appearance-wise and syntax driven up here. And there it is, 125 over 24, so we're good. Excellent. So the area between two functions here, y equals x cubed, y equals 36x. So if you actually graph that, there are two regions. They do happen to be equal area regions, but you do not have to know that, nor should you necessarily assume that if you're not, unless you're 100% sure. Work them out individually to be on the safe side. And you can, I'm not going to put the newer FNN technology on here because now you see what it looks like. So, but not too difficult here. But you see this one, you set this equation, x cubed equals 36x. One thing you never, ever want to do in math is divide by a variable unless you're sure that unless you're sure you can eliminate zero solutions, the zero as a solution, which is not true here. You don't ever divide by variable. So move the 36x over and then factor out an x because you'd lose this zero solution if you didn't do that. So x squared minus 36, we have 0, plus and minus 6, so those are the points of intersection. So our integral would just set up then, we're going from negative 6 to 0 with the curve on top. So we would have x cubed minus 36x. Then we'd go from 0 to 6 with the line on top of the curve, 36x minus x cubed. And so you put them in there. I did them separately. They are, it looks like I used zoom fit. The graph is really, well, yeah, I mean, if y equals x cubed, when x equals 6, y is going to be 216, so you definitely would have to, if you wanted to look at it visually, you would have to make some adjustments in the calculator to get it to look right. If you actually needed to see it, if you could do it without seeing it, that would be okay too. Which you probably could, but yeah. So let's see, to add the two pieces together, which I didn't show the individual areas. I'm sure they're both 324 separately. If you add them together, you'll get 648. All right. Okay, here's one where the area is already shaded for us. Everything's sort of done, so not too much work here. Other than you can kind of see the points of intersection, but I verified them mathematically up here. But set them equal, solve them, and you get it. It just verifies that it is -2 and +1 are the two x values where these graphs intersect. And but it's kind of obvious that's what it was. The parabola x squared minus 4, you can see is the upper parabola here, and then the 2x squared parabola is the lower. So technically, to do this in the right order, you would put the x squared minus 4 first, and the 2x squared plus x minus 6 second. And from -2 to 1, I use the F and N. I mean, these aren't hard to do if you're not using a fancy calculator. I shouldn't assume, meaning applying you have to do them that way. But you could do them, using basic antiderivatives there. I just sort of skipped that for the purposes of this review. I just didn't do it that way. But yeah, I'll just say this verbally. Yeah, you could integrate this and get negative x cubed over 3 minus negative x squared over 2 plus 2x. Plug in 1, work that out. Plug in -2, work that out. Subtract, and you'll end up with 9/2. Yeah, so I didn't want to imply that it can only be done by technology. Not at all. 9/2. Very good. So let's see what's next here. Not sure this is. Yeah, that was 15. So now we're looking for 16. And number 16, volume of a solid of revolution. Sometimes this can give people some trouble. Not so much the mathematics or the integration part of it's not difficult. It's setting it up properly and determining whether it's a disk or a washer. Washer meaning, is there a gap in it when it revolves around? Yeah, that's what. Usually the biggest mistake I see people do this is when it is a washer, they don't treat it as a washer. This one is not, because here's the sketch Now I couldn't sketch x equals 5, a vertical line, so I just drew it. X equals 0, y equals x squared, bounded by y equals 0, and x equals 0 over here. So that one hardly seems necessary, but that's okay. But anyway, that's good enough. So it's this shaded region right here. So this, as this graph revolves around the x-axis, you can see there would be no gap because it would come around, it would look like this, and it would be 100% solid all the way around. But just to give you an example, now let me look ahead here. I got a feeling I'm going to say this and watch it turn out being the exact same problem, next problem. Sometimes I do that. No, I did not do that, so now I'll go back and say it. Is if you revolve this around the y-axis here, it would be a washer because you would have this would swirl around with a gap in the middle. So you would have to do outer volume minus inner volume. And I'll just tell you in a minute here what that would set up like after we finish this. So this one's a complete solid. So you have, there's the formula pi and then lower and upper x values here. And so it would be the function x squared squared. And let's see, so it's x to the fourth. So real easy, integrate this. Pi times integral from 0 to 5 of x to the fourth. It's pretty easy. I'll just work that one out real quick. You can do the f and n. If you do the f and n, I would suggest, especially the answers all having pi in it, I would do the integral without pi, and don't put the pi that way. Well, it's no big deal, but you would have to then convert all these to decimals if you didn't do that. And that's kind of a pain. So, but if you do this integral without the pi, you'll get 625, and you would know it was 625 pi. But if this function's going around the y-axis, well, actually, you know what? Instead of just telling you this problem, the next one's going to pretty much solve our situation there. So you'll see it right here. So this will be good enough. Number 17. Y equals x cubed, the line x equals 4, it's going around the y-axis, so you're going to have a gap. So the outer volume edge would be the vertical line, and the inner would be the parabola. So what we're effectively doing is we're treating it as if that solid line was revolving all the way around, and we're calculating that volume, which actually is a cylinder, and then we're subtracting off this inside part. So the entire volume minus the inside leaves us right what we want right here. So by subtraction, we're getting what we want here. But around the y-axis, though, we have to integrate this as a function of y. So what we have to do is take y equals x cubed and solve it for x in terms of y, which is just a matter of cube rooting it. And so we're going to have y equals 1 cubed. Now the limits of integration will be on the y-axis. Now telling us that x equals 4, so we don't actually use 4 in the integral here. We would if it was going around the x-axis, but no trouble. If x equals 4 and y equals x cubed, then we know that y is going to be 64 whenever x is 4. So vertically here, the limits of integration are 0 to 64. The outer function is just x equals 4, so it's 4 squared. The inner is x equals y to the 1/3, so it's 4 squared minus y to the 1/3 squared. So we have the integral of 16 minus y to the 2/3, which will be, which you could do this in the calculator, but so you have 16y, and the antiderivative of y to the 2/3 is 3/5 y to the 5/3. Put in 64, put in 0, and here I'm kind of showing you what the individual fractions are, but you will get 2048 over 5 times pi is answer B. Okay, doke. Now we're getting into some spring problems. Okay. Now it takes a force of 1,300 pounds to compress a spring from a height of 1 inch to a compressed height of 6 inches. So that means we're moving it a total of 5 inches. So that's where this 5 comes from. It comes from 6 minus 1. So we're trying to, we need to get this K using the force 1300 equals 5 times K. And then K is going to be 2600. So these are actually, obviously, once you get it set up right, the functions are easy to integrate because you're just integrating f of x dx, the force function, kx dx basically. So 2600x dx from 0 to 1, compressing at the first inch would mean from length 0 to length 1. Or you're moving it in from 0 to 1. I shouldn't say length, that's not correct, but compressing, you're moving it 1 inch. So 1300x squared, antiderivative of 2600x, from 1 to 0 would be 1300 inch pounds are the units here. Now, surprised I didn't have one of those problems where you look back at the first exam stuff. I'm not sure if this, it depends on whether this is on the problem list for your final or not. But the ones that are, let's say if a spring was, let's say if it was 12 inches long and you're compressing it from a length of 5 to a length of 9, where you have to subtract, means if it's a length of 5 and it's a 12-inch spring, that means it's been compressed 7 inches. And when it was a length of 9 and it was 12, it means it's compressed 3. So the limits would go from 3 to 7. All right. Sometimes that's about the only tricky kind of stuff you can have with these problems. So if this is on your problem list, if it's not on there, then don't worry about it. But if it is, think about that too. So, all right, integration by parts. X squared e to the 2x. This is a nice basic one. You can do this by integration by parts twice, in case you forget this tabular method. You do it manually twice, no problem. But I think the tabular works out pretty well. So let's see what we have here. So the u is going to be the x term for these. It's going to be x squared. And then we take the derivatives down until we get the constant. So it goes x squared, 2x, 2. And remember, we have that sign chart we have to use. Plus, minus, plus. So it keeps alternating. Plus, minus, plus. Now, for the dv is e to the 2x. Be careful here that you're taking the antiderivative of e to the 2x, not the derivative. That's a common mistake I see people make, is they'll go from e to the 2x, and they'll go 2e to the 2x here instead of 1/2. So basically, you're multiplying every one of these by 1/2. So you get 1/2, and then 1/4, 1/8, and then you connect the lines this way. And we multiply, and these are your terms. So it'll be 1/2 x squared e to the 2x. And then we have a minus 2x times 1/4 e to the 2x. And of course that would reduce to 1/2. And then we have 2 times 1/8 e to the 2x. So that's 1/4 e to the 2x. And then our plus c. And then that matches answer A. Plus for the first term, then minus, then plus. So. All right, so there we have our answer. And let's take a look at this one, number 20. X cubed ln of 3x. Now, parts is not necessary. Tabular method for parts is not necessary here, because whenever you have x times ln, you're only going to need to do integration by parts once anyway. So you don't really necessarily have to use the tabular method for only one step here. But what is important to remember now is that your u changes for these. when x is combined with e, sine, and cosine, your u will be the x. Whenever it's combined with x is combined with ln or arctan or arc something, the u will be the arc something, the dv will be the dx. So here the dv is x cubed dx. All right, let's see. And then the antiderivative of x cubed, of course, would be x to the fourth. Okay. And then u is ln of 3x. And then du would actually be 1 over x dx. You might think by looking at it, it would be 3 over x, but it would not. If you wrote it out, you would see. That's why the eyeball test wouldn't be too good here. Because actually the derivative of ln of 3x would be 3 over 3x, which makes it 1 over x. So I use the parts formula, uv, so it would be 1/4 x to the fourth ln of 3x. So we're through with that part. And then now we have to integrate the other part, which just reduces to x's, so it's not difficult. So essentially you have an x to the 4 over 4 multiplied by a 1 over x, so I just kind of reordered the terms there. And you have x to the fourth divided by x, so essentially you're integrating 1/4 x cubed. So that would be antiderivative x cubed, of course, would be x to the 4 over 4. So you have a 1/4 and another 1/4, which makes it 1/16 x to the fourth plus c, along with the first part. So it's clearly answer B. All right, not too bad. Now, arc cosine of x dx. Now, you might say, hey, I don't see an x term here. You said I said the u had to be the arc. Well, if you don't see an x term, that means dv is just dx. If there's a power, if there's x raised to a power there, then you would use it. But if not, dv is just dx. So the antiderivative of dx is x. And then if u is arc cosine of x, the derivative would be -1 over the square root of 1 minus x squared dx. And then there we go. So we have that set up. Now let's see. So uv, multiply these two together, will be x arc cosine of x minus the integral of v du, which is -x, because you multiply these together over the square root of 1 minus x squared. So since those were two negatives, I went ahead and changed them to positive. Now you got to be careful here. Well, I guess since in this case, the answers aren't there, but I still want to mention this just to help you out. But a lot of people might look at that and think that that integral is going to be arc sine. Now, if there was not an x up in the numerator, or if it was just a constant, in other words, if there was a constant, it would be arc sine. With x, we can do u-substitution. Any power higher than that would have to be trig substitution. Technically, you can do trig substitution for this one. But who wants to do that when you can just do u-substitutions? Yeah, I'm not recommending that. But if you let u equal 1 minus x squared, you get du equals -2x dx. And then divide the -2 over, so you have -1/2 du. So you have the antiderivative then, and you bring this up, makes it negative power. So it's -1/2 u to the -1/2 du. And you work this out, you get -1/2 plus 1 over 1/2. The 1/2s cancel, the negative doesn't cancel, but the 1/2s would cancel, so you would have a -1 here, and then u to the positive 1/2. You can write all that out for yourself. I'm not saying you have to do all that I just said in your head, but write it out. I just kind of left out some steps like that. So basically you just have -u to the 1/2, so this problem just now turns back to negative. So you have x arc cosine of x minus the square root of 1 minus x squared plus c. So it will be answer C. Let's take a look at this one, number 22, 6 times cosine cubed of 3x. So this is one of the deals where you have cosine odd and positive, means you have to save one of the cosines. So in this case, we take away a cosine, that leaves cosine squared, and then we convert cosine squared into 1 minus sine squared. So we have a cos of 3x, and then a 1 minus sine squared of 3x. And so I went ahead and split this up. Technically, I don't know why I split this up. You don't really have to. Yeah, I don't know why I did that. It's correct, but a lot of my examples in my notes I did, and I would have just left it like this, 1 minus u squared, like that, because they're sharing the same du here. So I don't know why I did that, but it's not wrong. That's the important thing. So if you like to split them up, go with that. If you don't, like my other ones in my notes and whatnot, you don't have to do it. So the antiderivative of cosine of 3x would just be 1/3 sine of 3x. Now over here, I'm letting u be sine of 3x, so the derivative will be 3 cosine of 3x, so that means I have to divide both sides by 3. I didn't show that step, but when you divide both sides by 3, that's where this 1/3 is coming from right here. I kind of skipped a couple steps here. I guess I figured since we're a little more experienced by this time in the semester. But so this would have been u squared right here, which would have given me 1/3 u cubed. So there's that. So it's u cubed over 3. So then u, of course, is sine of 3x. So I have 6 times 1/3 times sine cubed of 3x over 3. So 6 over 3 is 2. And, oh, that's a mistake. I have the right answer checked, but I have 9 written here. So this should be 2/3. I'm assuming people might have just noticed that and maybe didn't tell me because it wasn't, even though I was wrong here, I had the wrong answers, that you could look at it and see that, oh, yeah, you could figure it out yourself. Oh, yeah, it's 2/3. And go, he just had a brain fart right there, which is what happened. Yeah, so perfect. Matches that answer beautifully. 3 times cosine of 4th of 6x. Now this one, you have to split this up as cosine squared times cosine squared. Then we have to use those special identities for cosine squared, not 1 minus sine squared like we used before. We had that special integrating identity that says cosine squared of x equals 1 plus cosine of 2x all divided by 2. So anyway, but you have to double your angle. So in this case, cosine squared of 6x would be 1 plus cosine of 12x divided by 2, and that's squared. So the 2 squared on bottom makes a 4, which I just brought out with a 3. Now you FOIL this out, you're going to get 1 plus 2 cosine of 12x plus cosine squared of 12x. Now the cosine squared of 12x means I'm going to have to use that identity again. So cosine squared of 12x means I'm going to get 1 plus cosine of 24x over 2. Now what I'm doing right here, since I know I'm going to have this one part that's divided by 2, I decide to make everything divided by 2 to get a common denominator. So you see I multiplied 1 by 2 over 2. There's 2 over 2. And this becomes 4 cosine of 12x divided by 2. So I wanted everything over that same 2. Everything's over 2, which I can then bring the 2 out with the 4, make that an 8. And then what's left up here, I can add the 2 and the 1 together before I integrate. I always like to, it's more efficient to sort of add your like terms together before you take the antiderivative. It's not wrong if you don't, it's just more efficient to do it. So 2 plus 1, that's usually 3. So now we're integrating this term, so now we got rid of all the squares, so we don't have to worry about using that identity anymore. So now we have the antiderivative of 3 would be 3x. Antiderivative of cos of 12x would be sine of 12x divided by 12. Of course, the 4 is in front. And then antiderivative cos of 24x would be sine of 24x over 24. Now we have that 3/8 on the outside that needs to be distributed through, and we'll get this 9/8x plus 1/8 sine of 12x plus 1/64 sine of 24x plus c. After, when you multiply and reduce all the fractions, that's what you get. And look and see, and that matches beautifully here with answer D. Number 24, 7 secant fourth of x dx. Secant fourth, whenever secant's odd and positive, we have a special recipe for that. That means we break it down into secant squared, and unlike the cosine squared, we don't have to use a special identity for that, because secant squared is good because that's already a du, because it's the derivative of tangent. So what you do is, so what I've done here is I've split this up as 2 secant squareds. I didn't write this one on the left as secant squared, but then I immediately rewrote this first secant squared as 1 plus tan squared. So I have 1 plus tan squared sec squared, and then where u is tan x, du is sec squared dx, so no adjustments need to be made to the du. Now once again, I split this one up when I could have just left it as 1 plus u squared inside there. Once again, so I don't know why I did that, but it's okay. So here I have 7 times sec squared of x dx. So antiderivative of sec squared is tan. This one you would do a u-substitution, so you're basically just integrating, 7 in front, u squared du. All right, which gives you 7/3 u cubed. So u is tangent, so you have 7/3 tan cubed of x plus c. So there it is, all packaged together. Looks just like answer D. So that's terrific.